then I have one for you. I have a string of a certain length with what is going to be close enough to a point mass hanging at the end. When this is horizontal, I'm going to let go, and notice that it wraps around this lower bar. The question I'm asking is, where do I need to place that bar so that it just barely makes it over, as opposed to wrapping around several times as it did just then? So we can find it experimentally, easily enough in theory. So we raise this. That helps if I screw the right one. All right, so somewhere between those two is going to be the point. And so I've got a mass, we're going to consider it a point mass. And I've got a bar down here. The mass is going to basically swing around and then just where it barely go over. This length is L. This length here is D. And I want to find the relationship of D to L. And then we'll see how close we actually get to the correct answer. Now, this is a nice little problem because it involves not only energy concepts, but it involves projectile motion and centrifugal motion. Thank you. All right, so let's first start out with what's physically going to happen to this string. I mean, I have it tight right here, and I let go. What happens? Just describe what you see or saw.
It releases tension.
And what do you mean by that?
It's kind of I wanted to say slack, but it's kind of the same. Like it doesn't stay. I guess that also just means tension as well. Now I'm trying to figure out a way to put it to not use just different synonyms for tension.
I think you're on the right track here, if I understood what I've heard so far.
The string isn't taut the entire duration of
Okay. So we need to figure out at what point does the string is not tight anymore. And once that happens, it's a projectile motion problem. So let's assume that we've got some point. Since I wanted to make it over the bar, it's going to have to be somewhere over here. It's not going to get slack at this point, because if it gets slack at that point, that means that the mass wants to do something like that, which would keep the string tight also. So it's going to get slack somewhere in this region here, and I'm just going to label that angle theta, for lack of imagination. All right, so at this point right here, well, first off, what is this length? I guess there's my mass. Or there's my mass right there. What is this length?
L.
L is the distance from the top pivot point to the end of the string. So L would be that length. D is just that length. What is this length?
L minus D.
Yeah, all right. So we get L minus D. From an energy point of view, figure out how much energy is right here. See if we can figure out how fast it's going from an energy point of view. Why don't we just let h equal to 0 there? Or at the bottom, like, we have to pick h is equal to 0 somewhere. We need a reference. So when it first starts out, what kind of energy does it have?
Potential. Or
Okay.
Gravitational potential.
Better. All right, so my initial energy is just my gravitational potential. What's the formula?
I don't remember.
All right, so remember there's a relationship between work and energy. What's the formula for work?
Force times distance.
Let's improve that a little bit. Almost there. Not distance. Work is a scalar, force is a vector, displacement, and it's a dot product. Assuming the force is constant, and weight, we are assuming is constant over the small region, close enough. So remember that work is just force times displacement, and for every conservative force, there is a formula for potential energy. And so the conservative force in this case is weight, otherwise known as mg, and the distance we're talking about is h. This is a very crude, questionable derivation of it, but hopefully just as a memory trick, force times the distance we're talking about. All right, so it's mgh. I don't know the mass. The mass actually is irrelevant. We're going to keep it in terms of letters, and h, well, initially it's 0, just by definition, by where I decided to make my reference. At this point right here, we have to figure out the height. We have to figure out this distance right there. And what is that distance? I'm going to call it I. I'm going to call this 0. So this is 0, and probably a different color would work better. This is point 1, point 2, and we'll come up with other numbers as we need them. So the energy at point 0 is 0 because it's not moving, so kinetic energy is 0, and we define our potential energy to be 0 there. What is the energy at 1? Let's take it step by step. What are my two types of energy we're talking about?
Potential and kinetic.
Yeah. So I got kinetic at 1 plus my potential at 1. Formula for kinetic energy?
1/2 mv squared.
At 1. And the formula for potential energy?
MGV, or MGH.
Not the right response. That's the answer to the next question.
Gravitational.
Just negative,
No, you're going way complicated.
That's
If
wrong.
I ask you what's the formula for potential energy, the correct response is which one?
Oh,
okay,
What's the formula for potential energy?
which one?
All right, the one associated with weight or mg.
MGH.
There we go. All right. So 1. Again, assuming the mass is not changing as it goes, and assume the acceleration due to gravity is constant, that's equal to 0. Mass cancels out, as you would hope. H1 though, this is H1.
Would it be D minus the sine of, or D minus
Is it D minus?
the quantity L minus D times sine theta? So it'd be that. minus
So L minus D sine theta is this part right here.
that. Yes.
And you did D minus that. One tweak to it. Alright, so we're dealing with, that distance there is D, and then that distance there is L minus D sine theta.
Would need to be negative,
Yeah, it would be negative, because,
so we started at 0.
yeah, and below, it's not a matter of what we decide is positive, negative direction, direction of gravitational pull. If you're below where you started, it's gonna be a smaller number, and if that's 0, this has to be negative. Negative. So we have 1/2 V1 squared plus G times, I guess, bring that minus up front, negative G, D minus L minus D sine theta. 1, 2, 3. Equals 0. So for conservation of energy, we've got this formula right here. Ultimately, we need to figure out a speed at this point, then we can figure out a velocity. So our speed, V1 squared, is equal to, well, let's see, 2G D minus 2, sorry, add that over, yeah, minus 2G L minus D sine theta square root. And just a quick look to see if I screwed up the minus sign somewhere. So that gets added over, you multiply by 2, distribute. I think that's accurate. And at this point, the answer is obvious. All right, questions up to here? All right, now, we have another principle involved here because the rope is still tight. There is still tension in the string. At that point, which it starts to go slack. So, at that moment right there, we have centripetal motion. It's traveling in a circular arc of radius L minus D. And so, well, if we do a force diagram, what are the forces acting on this? Okay, when it's at that point right there.
Wait.
Tension.
At some angle theta. Anything else? Attention, weight. All right. Now, since that's the point at which the rope is suddenly going to become slack, what is the tension equal to? Or close enough for physics? After it passes that point, it's like this. What's the tension at that point?
0.
So at that point right there, when it's just about to go slack, what's the tension?
Very, very close to zero.
Yeah, good enough for physics. And so all I really care about is the weight at that point. And so I have weight acting down. I have my rope, or actually towards the center of the circle is in that direction, that angle there is theta. I need to figure out the component of the weight that is in the direction of acceleration, because my acceleration is that way. So I need to break weight up into its components. So this is the component here that's slowing it down, because it is slowing down as it goes up. And this is the component that's causing it to travel in a circle. So if this is mg, what is this component here? And we can go through the geometry of it, or let's see. If I make that a skinny angle. Which of these two angles is theta?
The bottom one.
I would think so, if I'm drawing it correctly. So therefore, this component, since this angle down here is theta, this component of it has got to be mg sine theta. So from energy, we have V1 is equal to this. From centripetal motion, I have mg sine theta is equal to mv1 squared over L minus D. So we have two equations here. G is known. D we're trying to figure out what the ratio of D to L. L we would know. We don't know theta. We don't know V1. So if I combine these two equations, I can come up with some relationship between L and D. Potentially. So if I just take our V1 squared equation over there, I get mg sine theta equals, oh, m's cancel out, equals 2gd minus 2gl minus d sine theta divided by L minus D. Doesn't look particularly nice yet. We have one other piece to bring into this. Questions up to here? The last little bit is I know that I just want to barely clear the bar. It's a projectile motion problem. So let's get a bit of some stuff. So I have this thing traveling at some speed v, or v1. that this length right here, well, what is that length? No, that's L minus D. That's theta.
L minus D cosine theta.
And this right here,
L minus D sine theta.
and I know G is acting down. Now it matters what's positive and negative direction. So why don't we just choose up to be positive? So we set up. I hat, J hat. We have our displacement, initial velocity, final velocity, acceleration, and time. I know that horizontally, well, actually, what will be the displacement horizontally?
L minus D cosine theta.
And vertically?
L minus D sine theta. Negative, excuse me.
My initial velocity, horizontal. And this angle here is theta.
D sine theta.
Yes.
B cosine theta prime, which is the same thing.
Yeah, V1 sine theta. And this one,